Our last talk of the session and also of the conference is Safe, Strong, and Tractable Relevance Analysis for Planning. It's by Patrick Haslam, Malte Helmert, and Anders Jonsson. And Anders is presenting the talk.
Okay, so I'm going to give you some quick background on this problem, then show you what our contribution is, and a few results from experiments, and then conclude. So just like the talk we saw on stubborn sets, the kind of relevance analysis we're looking at here is to try to remove irrelevant actions from the problem. But unlike the stubborn sets, we aim to do it as a pre-processing step. And we want this relevance analysis to have three properties. First, that it's safe, that you don't remove any actions that actually need to solve the problem, or alternatively to solve it optimally. To be strong, that it actually finds several or much of the relevant actions that the problem contains. And finally, that it's tractable, that you can do this in an efficient way. And it turns out that previous approaches to this problem typically do two of the three, but they don't achieve all these three properties. So the standard backchaining approach you can use to detect actions that you don't need, and this is safe and tractable, but not very strong. It doesn't tend to find many relevant actions. And there's this path-based relevance analysis, which we're going to base our work on by Scholz, which is safe and strong, but not tractable. So the aim here is to try to find an algorithm that achieves all three properties. The drawback or limitation of our current algorithm is that it's strong only when actions are unary. So I'm going to talk about that a bit later. So just to briefly recap what path-based relevance analysis is, it was proposed by Scholz in his PhD thesis. The idea is you take the domain transition graphs of variables, the graphs describing transition between the values of a variable, and you look at paths that can be replaced in these graphs by other paths. You look at the actions that only appear on those paths that can be replaced, you label them as irrelevant, and you try to remove them from the problem. Well, this is not the whole part of the story. This is what we focus on in this talk. This is not the whole part of the story, because you also have to determine which nodes of the DTGs to look at relevant paths. So to do that, there's an iterative algorithm that starts with the start and goal values of each variable, finds paths between those, then iterates until you reach a fixed point. I'm not going to be able to describe that algorithm in more detail. So the problem here in the original work was that the number of paths through a DTG can be exponential in the size of the DTG. So the approach is slow when the DTG is dense. So we're going to focus on this replaceability test, like I said. So for the moment, I'm going to assume that actions are unary. In that case, the transitions or paths in the DTGs can be fully characterized by the preconditions that the actions have on other variables, because the actions have no effects on other variables than the current one. And we can then define a subsumption relation between paths. So a path subsumes another one, which essentially means you can replace Q with P in this case. So I'll just give you a brief idea of how this works. So in this graph, the lower path can be replaced by the upper path, because whenever the precondition UV holds, then trivially U also holds. Whenever not U holds, the empty precondition holds, and whenever U not V holds, not V holds. So the upper path can always be applied whenever the lower path can. So if you have a plan where the lower path is in, you can replace that with the upper path instead. So if you want to do optimal planning, you need an additional condition, which is that the replacing path should not be longer than the replaceable path, because then you might increase action cost. So our contribution is to try to make this approach tractable by, instead of comparing all pairs of paths between two nodes, we're going to introduce lower and upper bounds on the set of all irreplaceable paths between two nodes of a DTG. The bounds are themselves paths. So a set of paths have a lower bound that's a path and an upper bound that's a path. These paths do not necessarily have to be actual paths in the DTG. And a set of paths is replaceable if their lower bound is subsumed by the upper bound on some other set of paths. Okay, that's the simple criteria that we're going to use. And this is approximate because this might miss some individual replaceable paths that you would find if you compared all pairs of paths. But as we're going to show, this is quicker both in theory and in practice. So how do we compute these lower and upper bounds? Well, we introduced two operations, namely intersection and union on paths. So the intersection between two paths P and Q is a path R that subsumes both P and Q, and the sum of the precondition sizes of this path is maximized. So the reason for the third condition is that we want the lower bound to be as rich as possible to increase the possibility or the probability that it can be subsumed by the upper bound on some other set of paths. Because, well, trivially, the empty path would subsume both P and Q, but it's not that rich in that sense. It's unlikely it would be subsumed by something else. And the union is just the converse on this. It's a path that's subsumed by both P and Q, and the precondition size is minimized. And so the lower bound is just going to be the intersection of all paths, and the upper bound will be the union on all paths. And we show that you can efficiently compute these operations using dynamic programming. So I'm not going to explain the details here. They are in the paper. So we're going to modify this replaceability test that I showed before in the following way. We're going to run a modified breadth-first search from the start node, then update the lower and upper bounds on irreplaceable paths from the start node to each other node. And the key that makes this tractable is that we only need to consider paths that don't contain loops in them. Because if they contain loop, we can just get rid of the part that comes back to the same value. And if we do that, then all upper bounds that are longer than the number of nodes of the graph can never subsume the lower bound on another set of paths. So we can put an upper bound on the number of times we have to do these operations. And the rest of the algorithm is exactly the same as before, the part where we determine which nodes to look for irreplaceable paths. Okay, so just a small example. So this is an artificial example where you have the start node is in the lower left. You have 5 actions corresponding to these preconditions, and if you say that you want to test for replaceability between the lower left node and the upper right node, then, well, there are only 3 paths in this case. So doing it for each pair of paths would not take that long in this case. But this is what our algorithm would do. So you would pick some edge of the graph from the start node. It would just append the precondition on that node in that case, and that would become the lower and upper bound of this node. Then it would do the same for the edge going upwards. If we now consider the edge going diagonally, the lower bound on this edge, or the lower bound traveling to the lower right node along this edge, would be the precondition UV, followed by not U. And this is subsumed by the upper bound on the lower edge, which is just U. So in this case, this edge is labeled as irrelevant, because it can be replaced. When you're going to the lower right node, it can be replaced by the bottom edge. Then you continue along some other edge, then you get the lower and upper bound is still the same. But if we now move from the top left node to the top right node, this is where our intersection and union operations come into play. So the lower bound becomes the largest path, in fact, that subsumes both the path going up and then right, and the path going right and then up. And similarly for the upper bound. Okay. So what happens if domains are non-unary? Well, the replaceability, if actions have effects on other variables, require the exact same sequence of effects on those variables, which is very restrictive. So in this case, the pruning power is significantly reduced because it's very unlikely that two paths will have exactly the same sequence on effects on other variables. So this is somewhat discouraging, but in some cases we can look at problem reformulation, looking at ways to take a non-unary domain and transform it so that it has unary actions. So there are different ways of doing this. And one way actually works well, combines well with our approach, and the other one does not. So the one that works well is taking, doing reformulation by introducing disjunctive preconditions of actions. So in fact, it's the same as saying you split an action into multiple actions, and now all of them have just one effect. And another one is to serialize the effects of action so that you now have to simulate an action, you have to perform a sequence of actions that each perform one of the effects of the original action. So in the first case, the reformulation allows you to just, the disjunctive precondition allows you to just perform one of these actions is sufficient. Okay, so just some brief experiments. So the setup we used, we did optimal planning in 4 benchmark domains, in logistics, myconic, blocks, and driver log. So logistics is the only one of these domains that has unary actions to begin with. In myconic, it's very easy to make a slight modification to the domain description to make actions unary. In blocks and driver log, we performed this problem reformulation, introducing disjunctive preconditions, which allowed us to make actions unary. And we ran fast downward to solve all the planning instances of these domains optimally. So this graph here shows the fraction of actions pruned in the 4 domains as a fraction of all the actions of the problem. So you can see that in blocks world, for example, this approach works very well. In fact, in some cases, we prune up to over 90% of the actions of the original problem. In the other domains, it's also reasonable. In driver log is where it works less well, but still we can prune up to 30% of the actions in some cases. So this, of course, has an impact on search because now the branching factor of search will be lower. So the next graph shows what the total planning time is with and without relevance analysis. In the x-axis, you have the total time for solving the original instance. In the y-axis, you have the total time with actions removed by relevance analysis. And well, if you squirt a little, you can see that the curve is going slightly below the diagonal, which means that the optimal planning is faster when you do relevance analysis. The time for relevance analysis includes the pre-processing time, which is usually quite small. And if you take a look at the number of instances solved, we can solve 10% more instances optimally with relevance analysis, and the total planning time on problem solved is 64% less. And we also compared our approach to the exact relevance analysis, where you compare all pairs of paths between 2 nodes. So in theory, this could find more irrelevant actions than our approach. But in practice, it only found few relevant actions in driver log and some instances of logistics. And more importantly, in no case did it result in more instances solved. But the exact analysis being intractable timed out in 54% of the instances. So it was not possible to run it in half of the instances. So that's where our algorithm really paid off. Okay, so to conclude, we suggested a novel approximate algorithm for relevance analysis. It's provably safe and tractable. we have an upper bound on the running time in the paper. It's proven to be strong in experiments for actions for domains with unary actions. It performs as well as the corresponding exact algorithm in practice, at least in the domains we tried. But it comes with its limitation that we haven't been able to solve, which is that it only works so far well. It's only strong. It's only proven many actions in benchmarks with unary actions. Okay, so that's it.